Alright, welcome to another AQAA-Level chemistry video. Today I'm going to be doing a video on weak acids and bases. Now, I made reference to this topic quite a lot in previous videos where I talked about the fact that we calculate weak acids and bases in a different way. And this is generally the topic that gives you the most marks because it requires most calculation. I'll leave a link in the description to Allery Chemistry's video that helped me a lot when answering these questions. This video isn't going to be like his, it's more going to be about understanding what is what in terms of what symbols represent it, what acid dissociation constants, how we work out acid dissociation constants, why we need acid dissociation constants. But it all falls down to the key principle of the fact that when we talked about in previous videos in regards to strong acid, we know that with strong acids, equilibrium is far to the right when considering dissociation of strong acids, right? So we can then therefore assume, so we know that strong acids strongly dissociate H plus ions in solution because the equilibrium is far to the right, and therefore we can make the assumption that the concentration of an acid, a strong acid, is the same as the concentration of a let me refer that. The concentration of a strong monoprotic acid is the same as the concentration of H plus ions in solution because it strongly dissociates H plus ions in solution. Any HCl that's there, for example, if you're using HCl, for example, as a monoprotic acid, the concentration of HCl in solution is the same as the concentration of H plus because it fully dissociates. And if we're talking about diprotic or triprotic, it'll just be times 2, right? It'll be the H plus concentration will be times 2 the acids, the concentration of acid in your solution, unassociated acid in solution. However, now that's really in regards to strong acids. With weak acids, I mean, if I just talk about weak monoprotic acid, the equilibrium isn't as far to the right. And now this is going to be a different thing, and I'm going to go straight into this video and talk about what this is. But we know that weak acids don't fully ionize in solution, so let me get straight into the video without waffling too much, and I can better explain this video. So, not all acids and bases fully dissociate in solution. Weak acids don't fully ionize in solution. So for a strong acid like HCl, the equilibrium for the following equation lies very far to the right. So HCl dissociating into H plus Cl minus, the equilibrium will be far to the right for that equation because it's a strong acid. Whereas for weak acids, for example, ethanoic acid, the equilibrium lies closer to the middle. So not very far right, not very far left. Obviously, it's definitely not going to be far left. It's going to be right, but it's more closer to the middle. It's not going to try and force that dissociation. And if you ever want to know what that dissociation would look like, it would look like this. Oh, I can't do that. Can I do it here? I can. This here, the equilibrium isn't far to the right. Here, this reaction, equilibrium is far to the right. Far to the right. Whereas it's slightly to the right in this reaction, is more closer to the middle. I.e., when it means it's that when in the middle, the reverse reaction is the same as the forward reaction in terms of the fact that it is slightly more to the right, but really dissociation isn't favored as much because it's a weak acid. It doesn't dissociate H plus ions greatly in solution, and some of them can reform back to reform the weak acid. So the key principle here is that dissociation isn't strong. So weak bases behave similarly. They don't fully ionize in solution. So weak bases follow the same. That's for weak acids, right? But for weak bases, they also follow a similar pattern where they don't fully ionize in solution. So for weak acids and bases, the concentration of H plus or the concentration of hydroxide ions isn't just the concentration of acids or bases. So we can't assume that the concentration of our weak base or weak acid is the same as concentration of H plus or OH minus in solution. And therefore, this makes it a bit harder to calculate the concentration in solution, right? How can we, if we want to work out the pH of something, even if we don't want to work a pH, if you just want to work out the H plus concentration, but I'll say pH because that's one of the things that we can calculate from H plus concentration, right? If you want to work out the pH, how are we going to work it out? Because easy to work out the H plus anyway, because we can't assume the concentration of our acid is the same as the concentration of H plus in solution. So we have to rework our understanding of this, right? So we can use something called an acid dissociation constant, which is referred to by Ka. We define a new constant as Ka is equal to H plus times by A minus over HA. And if you're ever thinking about why it's written as this, it's as simple as the fact that this reaction here, right? Any acid, so let's say we call it HCl HA. We refer to halides as A minus. So HA refers to unionized acid molecules. A minus refers to the anion remainder after loss of a proton, and obviously H plus represents the proton. So if we're saying HA, treat HA as HCl, for example, right? HA will be going for, will dissociate into H plus A minus, right? And this applies to all acids. It's just that we typically use this for when we're calculating weak acids and weak bases, because as I said, for strong acids, we know the concentration of a strong acid is the same as the H plus. So the concentration of the H plus concentration of a strong acid is the same as the concentration of the acid, really. So this isn't really necessary. But so if you want, we can make an equilibrium constant, right? This reaction is in equilibrium, therefore we can make another equilibrium constant. And remember, when we're doing equilibrium constant, it's products over reactants, and that's what we have here. Now, I think I've probably made it very clear. So if the A minus could be an OH minus, it could be a Cl minus, a Cn minus, so cyanide for group example, right? But the key principle being that you have your H plus representing the proton, and the A minus representing an anion, and the HA representing the unionized acid molecule. So in its unionized form, so it not being dissociated. So this is the Ka, which is the acid dissociation constant. Now, like all the acid dissociation constants, right? All acid dissociation constants are temperature dependent, but it's an equilibrium constant. But that's not really. I think it's pretty obvious by now when we're talking about acid dissociation constants, energy used to break bonds, all that. But that's fine. But one thing you need to be more aware of, and what it actually represents in solutions, that a large Ka value means a lot of acid is associated in solution, right? So if the Ka value is higher, equilibrium is shifted more to the right, and therefore there's more dissociation, and therefore it's regarded as being a stronger acid, because more acid has been or at least a stronger acid, because more acid is being more of those acid molecules are being dissociated in solution, right? And henceforth, a small Ka value means little acid ionizes in solution. Now we have Ka, right? Ka is that dissociation constant, allowing us to determine the number of Ka, the number of molecules, acid molecules, unionized. So Ka represents the number of unionized acid molecules that are dissociating in solution, right? The pKa, just like pH, we use pKa because Ka values vary a lot, right? We're talking, if I'm talking about, as I said, Ka represents the number of unionized acid molecules that are dissociating in solution. There's probably thousands or millions of those acid molecules that are dissociating in solution, which makes it so hard to, like, and it's like H plus concentration, right? It's so hard to then work out. So you use something called pKa, which is just a logarithmic term, the same as pH, or the same kind of principle as pH. So pKa is equal to minus log base 10 of your Ka, or as I said before in a previous video, you can also check out that video where it would have been the most recent video. No, it would have been 2 videos ago. Yeah, when I was talking about pH, yeah, 2 videos ago. In mathematics, a capital L refers to minus log base 10. So you can represent it like, if they ever ask you the definition of pKa, you need to understand that it could be you write out the equation. The mathematical equation is the definition. So pKa is equal to minus log base 10 of Ka, or you can write it like this as well. They don't penalize either way. So you can write pK is equal to minus with a capital L log Ka. And I've written it there just in case you can't read my handwriting. And just like Ka, right? Just like with H plus concentration and pH, converting pKa is equal to converting pKa to Ka it's also very easy to do. It's pretty much like the same principle as pH, right? The definition of pKa is pKa is equal to minus log base 10 of the Ka. We can rearrange that to be that Ka is equal to 10 to the power of minus pKa. As I said, I think you guys can already see the similarities, right? So pH is equal to minus log base 10 of our H plus concentration. And to work out the H plus concentration, is equal to 10 to the power of minus your pH. See similarities? Now, there are instances where pH is also just equal to your pKa. And I'm pretty sure in nearly all examples, if they're asking you to work out the pH and if only give you information to work for pKa, pKa and pH are the same. Now, I'm not going to go into how to prove that because I haven't read up on that one, but I do remember very well that pH is pretty much equal to pKa. There's like a little graph that you can use to represent that, but as I'll leave a link in the video to Allery Chemistry video. Allery Chemistry's videos were the ones that actually explained how to answer these topics very well. And I don't know if he said it in that particular video that I've left in the link in the description, but hopefully it's the one. But yeah, I'll move on now. So calculating H plus from Ka. When you dissolve a weak monoprotic acid in solution, H plus is always equal to A minus. And this means you can simplify the Ka into this equation here. So when you dissolve a really weak monoprotic acid in solution, because the concentration of H plus is so weak, because we go back to this equation here, right? We go back to this equation here. Right? If this is a weak solution, so a weak acid, will not dissociate. Weak acids don't strongly dissociate H plus ions in solution. We can then assume that the H plus concentration is equal to the A minus concentration. It's that weak. And if that's the case, it's pretty much the same as doing H plus squared. We can then rearrange this to say that in a really weak acid, when dissolving a weak monoprotic acid in solution, this is one of the equations that we can use. Because they might not give, if they say it's a weak acid, they don't give you the OH minus, and they need you to work out the Ka. And if they've given you enough information to work out the concentration of the unionized acid, and they've given you enough information to work out the concentration of H plus, that should be H plus. I need you to work out Ka. You can assume that the concentration of H plus is equal to concentration of A minus, and Ka is equal to, therefore, Ka would be equal to H plus squared over Ha. And Ka being acid dissociation constant, H plus representing the concentration of protons, and Ha representing the concentration of unionized molecules. I don't know why I left this here. This doesn't need to be here. Sorry about that. But Ha is the concentration of acid. Ha is the concentration of the acid added. So there are situations where you can make a buffer, or you add acids to your solution. And Ha is the concentration of acid that's added. So Ha minus the concentration of ionized acid, because if we're making we may have a solution where we have strong acids and we have a strong acid, and and just maybe a weak acid or some sort of other solution that's involved, and we need to work out the uh the concentration of HA by itself. If you want to work out the concentration of acid that's left over, right, we would have to do HA minus H plus, essentially. I think it's very, very confusing what I've said here. Or I'll represent this by, there may be instances, right, in your solution where you have a really strong acid and you have some sort of salt. And this is a weak salt of some sort, right? Or weak acid, something like that. And you have a strong acid here. So that's H plus. So this is essentially your just H plus solution, right? We're now taking that away. We want to just work out what HA is by itself. All we're doing is HA minus H plus. And by H plus, I say HA0. That's just representing maybe a salt. If you want to just get HA by itself, this is essentially, this here is essentially this. It's just this, but we've just trying to make it easier for us to work out what HA is. And if we want to work out where's that? Yeah. If we want to work out what this is, we need to take away essentially all of this minus this. That's what we have. We know what this is here. We know what this is here. If you want to work out just this here, that's what we're doing here. HA minus H plus. Now, this doesn't make much sense to you because you're just confusing me a whole lot more. Again, watch a YouTube video that I'll leave in the link. Well, watch Allery Chemistry. He'll explain more about this, and I'll probably go into this more when I do the next topic, which is to do with pH curves and titrations. But this is just part of your calculation process to allow you to work out your Ka, and it's not as straightforward as just what is the HA, what's the H plus. There may be times where you need to take away values in order to work out a value that you're going to sub into an equation, right? The same way how they don't always give you the concentration, you have to work out the concentration. And that's all it is. If this has confused you, don't worry. Watch a video on Allery Chemistry that'll help you better understand that topic. It's something that's more going into buffer solutions, really. So I understand if this is kind of confused you. Because, yeah, I probably shouldn't have done the Seneca part of this part, because I've realized now it's probably confusing people. So yeah, if you know the values of Ka and Ha0, you can calculate the concentration of H plus ions. Calculating, why is it calculating? Calculating the HA from Ka and pH. This here is just a rearrangement. So first use the definition of pH to calculate the H plus. So if they want you to work out the concentration of HA in solution, and they've given you the pH, right? So they've given you pH, they've given you the acid dissociation constant. If they've given you pH, you know that if I need to work out the HA. I know that HA is equal to, first of all, I know that Ka is equal to H plus squared over HA. This is a weak acid that they told you. They told you they want you to work out the HA of a weak acid, the concentration of a weak acid, essentially. And they've given you the pH and they've given you the acid dissociation constant. So the first thing I do here is that I'd write Ka is equal to H plus squared over HA. Now, how am I going to work out HA? Well, first of all, so how am I going to work out, rearrange this? I need to work out HA, so I need to rearrange this equation to HA, that's a terrible square bracket. HA is equal to H plus squared over, again, my square brackets are horrendous. H plus squared over Ka. Okay, I have given us Ka, but I haven't got H plus. But they've given me the pH. I remember that the H plus concentration is equal to 10 to the power of minus your pH. Therefore, we found our H plus concentration. We substitute our values in, and that's all it is. That's all that's happening here. Right, that's the end of this video. Hopefully, I haven't confused you too much. I probably have confused you more. Forget about this last part here. Forget about this last part here. Everything I told you up until that point is the more important part that you need to learn. This part here will just come with time, but it's about in understanding what HA, what Ka, what A minus, what that equation was all about. Where have I even left it? The understanding how Ka forms, what Ka represents. Remember, Ka representing the number of unionized acid molecules that are dissociating in solution, or really the equilibrium constant that's representing how likely the equilibrium will shift to the right for dissociation. And that's it, really. Hopefully this